questions on any homework problems?
Do you ever remember
Number one, can you tell me something about it?
it was other series and also the first six? Also the first six.
So is this on 6.1B, the online homework?
Yeah.
Okay. So let me look it up here. Number one, Julian. Ah, 7/1 plus 64x squared. That's the problem I got. You probably got a different one. That's not it. Okay. So we figured out on Friday that the function 1/1 plus x can be written as the power series this way. Okay. I could go one step further. Because of this square, I should have noticed it. We're just going to compose this function with x squared, so all the x's will double powers. Okay? And then 64, well, I want to compose this function with the function 8x. When you square 8x, you get 64x. So wherever the x's show up, plug in 8x. And finally, I'm just going to multiply through by 7. Now let me read the question. C0 through C4. C0 is the constant term. Find the radius of convergence. All right, C0 is 1. C1 is 0. There is no x term. Right? If you look at the formula they give us, call them C's. It's like they don't skip the odd powers because, you know, maybe we don't need to. That is, they let us figure out. Odd powers are going to have a coefficient of 0. C2 is, oh wait, we've got to multiply through by 7. C2 is minus 64 times 7. The coefficient of x squared after we multiply through by 7. C3 is 0. C4 is 7 times 8 to the 4th. Okay, and they also ask for the radius of convergence. Well, we know the series we started with converges on -1 to 1. And then we're going to compose it with 8x. So it's going to converge as long as the thing we're plugging in, 8x, is between -1 and 1. And divide by 8. R equals 1/8. So C0 is 7, right? C1 is 0. I'll just check and see, make sure I'm giving you good advice. Minus 7 times, what's C2? 64. Oops. I'll let the system multiply it, but I need the multiplication sign. C3 is?
0.
C4 is 7 times 8 to the 4th.
Yep.
And the radius of convergence is 1/8. And submit. It doesn't like the third one.
Should it be positive?
Preview. Oh. I wrote bad syntax. It says not a valid fraction. My explanation is right because all the rest of them are green. Why do you want a fraction?
I got the whole number.
Oh, tell me that.
It should be negative 448.
7 times 64.
Yeah.
Boom. Oh, that's it. So why doesn't, I guess it doesn't let you do it won't do the arithmetic for you. Okay, Julian? All right. Any other questions? So you see how we use the series we wrote on the sideboard, just dig into new ones. As long as they're reasonably similar. And I guess reasonable is in the eye of the beholder, but hopefully we'll develop some skill. Okay, no other questions? So let's review for the exam, and then I want us to look at some things on the XYZ side, just so you know what all is there. So exam 3 on Wednesday. The format details are the same, which means there's a strict time limit. It means we show all necessary work, grade the work, not the answer. Although, if I ask an obvious, simple question, it's a little different. No calculator, just focus on the concepts. You won't need one. On the exam, if the answer is 7 times 64, you can just write that. Okay, I'll analyze your arithmetic. And you can bring a 3x5 note. I was thinking the other day that it might be better for you if I didn't, but I think everybody likes to have it. So the material, we've covered chapter 5 and parts of 6. Of course, chapter 5 is all about just infinite series, and chapter 6 about power series. And let's just review. We started off with the section on sequences. This is just a list of numbers, one for every positive integer. And all we really cared about was, does the sequence approach a number as we move down it, or does it not? We call that number, if there is one, a limit. And we use words like decreasing, increasing. We talked about bounded a little bit. Those words all convey the obvious meaning. And then we really don't care about sequences so much, we care about series. But the only way that we can really handle series and infinite sum is through its sequence of partial sums. So we say the sum of the series is the limit. This is our definition of the sequence of partial sums. That's what Sn is. It's exactly what it says. Like, as n goes, we just sum up more of it. And then we want to know, what happens if we keep doing it without stopping? Sequence of partial sums. That's the definition of the sum of the series. We never actually add the numbers together. And we can actually analyze the sequence of partial sums for a very important class of series, geometric. Probably the very important. We can answer any question that anyone would ever ask about geometric series. We know them completely. When they converge, we can find the value they converge to. We know exactly when they diverge. We're experts. And, I haven't made the test out yet, and I probably won't count the points up. But my guess is, showing me your knowledge of geometric series could earn you maybe 20% of the points on the exam, just one topic. Just today, I got an email from a student in the morning class, asked me about number 3, not number 1. And I don't know if you've done number 3 yet. There are lots of ways, maybe a guy can do it, but if you look at it, it's a geometric series. Like, as soon as we recognize that, it's easy. We know, if you know it's geometric, you know the value of R. If it's between -1 and 1, it converges. If it's not, it diverges. It converges always to the first term. So when it does converge, over 1 minus R, super useful. But then we don't have to worry about where the sum starts. We don't have to write it in perfect form. We recognize it's geometric. We get a value of R is between -1 and 1, and then we just plug in that beginning index value. That's the first term. And divide by 1 minus R. There were some isolated few cases where, remember, the sequence of partial sums with telescope. But we really weren't very scientific about that. And they are not that important. And there could be a question on the exam. I will guarantee you'll have ample opportunity to use your knowledge of geometric series on the exam. I think there's a good chance there will be a question about the sequence of partial sums as well. All right, and then for a long time, we just focused on the tests, convergence tests. We got a bunch of them. So let's list them all out here. Think about how to format your 3x5 part. We could analyze Sn. It was rare, but we did it at least twice. I think you did it once on the homework as well. And then we're going to put like geometric series. It's not really a test, but we can decide if the series converges or not. And in these two cases, we can find the sum. And none of the others can we find the sum. They're just going to tell us if they work, converge or diverge. The third case, the first. The divergence test, followed closely by the integral test. Special subcategory from the integral test, P-series. Number 5, comparison test. All right, plural, there are 2. The straightforward comparison and the limit comparison. We like the limit comparison better most of the time. The alternating series test only works on alternating series. And number 7, the ratio. Number 8, the root. Yeah, I thought there were more than 8. I think I left one out, but there are 2 of them. That's one. That's what I did. Okay. Probably, just given the size of an exam, when there is a strict time limit, probably won't need to use all of those, but you certainly will need to use some of them. Most of the time, I'll let you choose the test. We can have a series where lots of different tests might work. I may tell you, use this test for this one, or I may not. I'm probably less likely to tell you exactly what you decide. All right, and then we looked at some power series, which is A and X to the n. And we were focused on the question, like, for what X does it converge? And we discovered there are exactly 3 possibilities. The first one is only at 0. And in each case, we identified something called the radius of convergence. And the first case, if it only converges at 0, it's not really an infinite series. It's totally boring. It's something that could happen. It's not ever going to be useful to us, but we're recognizing it happens. Second one, everywhere, it converges for every real number. In which case we write R equals infinity. And the third case, the problem that Julian asked about, it converges on an interval from minus R to R. And possibly at the endpoints. We have to investigate. And R is the radius, the symbol I use here. Radius of convergence. Okay, and we looked briefly, and we could do it briefly because it turned out we could use what we learned here to solve it. That is power series centered at some number other than 0. So say the number A. Then the 3 possibilities, converges only for X equals A, in which case R is 0. Second one, everywhere is everywhere. And the third one, it would converge from A minus R to A plus R. R equals the radius. And possibly at the endpoint, we have to investigate. Okay. My advice was, if you see one of these, to just let U be X minus A, and then use what we learned about power series centered at 0, solve the problem, and then move if you get this category, just move the interval over. Take it.
What is X? It's 1 for 1. It says X
Equals A.
Oh, okay.
Yeah, and whoever watches this recording will appreciate you asking that question. Okay. And then we learned once we learned the basics here, then we started finding the function actually for x's where the series converges. We can think of this thing as a function of x. And then we were able to learn power series for various functions. Special, we'll call them series. 1 over 1 minus x. Everything started with this one. It's just the geometry. And then we learned how to change that sign by composing it. function. We learned how to turn that x into a square. We learned how to turn this one into the log of 1 plus x by integrating, as well as 1 over 1 plus x squared. We could find a series for the inverse tangent. Okay, I didn't write them all out. I made a mistake. I skipped over the x term. Maybe some of you were wondering. Good for you. There's also the interval of convergence on all of these. Converges on -1, 1. The radius is 1. Some of them converge at the endpoints. So here we're plugging in x squared into this one. Here we're integrating that one. X minus 1/2 x squared plus 1/3 x cubed. Here we're integrating that. X minus 1/3 x cubed plus 1/5 x to the 5th. You know, and we could plug in the 64 with that x, just like we did on problem number 1 on the whole. Very question.
For the thing all of those converge to, what does that say? In parentheses.
Where am I looking?
Oh.
Oh, what does this say?
Yeah, I got it now.
Okay, -1 to 1, all of these. Ln 1 plus x and inverse tangent also converge at the right-hand endpoint by the alternating series test. 1 minus 1/2 plus 1/3, that's the alternating harmonic, which we know converges, and this one's very similar, hitting only the odd. So all of these converge on the interval -1 to 1, and I think just those two converge at 1. Yeah, those are clearly not going to converge. Good grief, what a mess I made. Okay, any other questions? All right, I want to take a look at the XYZ system and show you some things I've made available to you there. If you're watching the video, I'm not sure that I can record the screen in front of the classroom. I think if I put it on record the desktop, I'm talking to them, not you all. You'll be able to see it, that's fine. I think it's going to record my computer screen. We'll see. So I'll leave the recording going and you can at least hear my voice and you can know what's available. If I can't find a way to actually record the screen at the front of the room. Victoria, could you flip one of those, whichever light is the front of the room? Perfect. Thank you. So how about if I slide this over and then I record the screen? No, that's not going to work. It's going to have my big face in front of it, won't it?
Do the share screen.
Won't grab it. There we go. Okay, so tell me what to do.
You can do it.
Like share screen here? And do you think it'll, what, will show this screen or my computer screen?
If you brought your face back up, and share screen.
You think I need my face back over here? Face is gonna get tired of moving around. Okay, now we share screen.
Yeah.
I did this once before and I discovered that
To
Right.
desktop.
right there.
Or you Firefox. But now.
Thank you. All right, so let's go back to the. Yeah, I think I've told you. Yeah, if I haven't, I'll tell you now, it's true either way, that there are a lot of topics in this section of material that the online homework just does not do a good job. Some of them it ignores completely. For example, what us calc professor would say, the very important one, the ratio test. Like there are almost no, maybe no homework problems dealing with it. That's terrible. I wish it wasn't the case. And so I have added a lot of stuff. And what I referred to that I've told you before, I think, and I'll tell you again, is that, you know, if you come here to the exam on Wednesday and you can do problems like all of the problems on the XYZ homework system, then, you know, maybe you're in condition to get like a D plus or a C, because it just doesn't cover everything. And as you know, I've tried to give you lots of extra things. I've tried to help you by working problems. All right, a year ago, when COVID hit, just about the middle of March, we sent everybody home. And we did all of our teaching remotely. And I had Calc 2 then as well. And one of the students, I sent her an email, like her final exam just was beautifully written and I wanted her to know it. And she said, well, I expected her to say, oh, well, you just explained it so well. But she said, well, I found a video on YouTube that really helped me. And so I went back and found it. And here it is. I think you have to deal with 5 seconds of a commercial. One of our graduates is a actuary for Liberty Mutual. Makes a ton
Hey
of
guys,
money.
does this day sound familiar? You go to a confusing lecture, you ask for help.
So here it is. What test should we use? Like
One of the
just,
hardest things for
here, this
students
guy
when they're
has what,
first being
8
introduced
different
to
series, and he talks
series
about a
is,
strategy.
how do I know
And
which
we've done
test
some of
to
that.
use
Like if
or
there's a
which kind
factorial
of
involved,
series?
we're
There's
gonna
so
first thing
many
we're gonna
different
think of
tests out
is
there. And see,
the
what
ratio
I'm
test.
doing in
Right?
this video is I'm giving you
And we'll
8
never ever
different
think of
series.
the
We're
integral
doing
test.
a matching game to
So
figure out
you know, watch
what
it,
kind
see
of
if it
test should I apply to which series. And then all the way at the
can
end of the
help you
video, I'm
out.
going to step off the
And
screen and
then
I'm just going to put up the
let's check
full
all that.
answers for each of those. And if you
And we'll go back over here. So look at all the things. Here are some practice problems I put on. There's just a whole page full of these. They're, you know, they're fun problems to try to solve. And in a minute, maybe we'll look at some. But those are practice. I didn't identify any of them. Here, exercise 4.2, the material we covered, there were no online homework problems. And here I've assigned 4 of them, 3, 4, 8, and 13. Probably all of them are, you know, good problems. Yeah, maybe not. Pay attention to the ones I assigned on that one. And there's a video from class, and then the problems online that we are due today, and another class. And then here we have power series. There's a whole slew of problems in this file, and then I posted 4 solutions and 1 partial solution. I'd be more than happy to post the solution to any problem if you think it would help you. And just let me know. I like solving problems. And then we have, like I said, the ratio test. It just don't give us any good ones. Here are a bunch of problems again. And I've identified specifically the ones that the ratio test will have. I mostly posted this for you to practice on the ratio test. And I wanted you to know, like maybe not all of them work, but 5 of them will. So take a look at those. Another online homework, another video from the class. I think I made a mistake in one of my classes and I tried to correct it there. Alternating series, here are some practice problems, 3 solutions posted. I think there's more comparison problems. problems posted here, 2 solutions, hints for the rest. I think I tell you how many of them diverge. Yeah, each problem, the ones that I haven't posted solutions for. And I've given you an idea of a test that you can use. I think that might be it for supplementary. Oh no, here's some more. Like, do they converge or diverge? So there is no shortage of things for you to practice on. I will not ask a dice problem on this test. We don't know enough probability theory. I just thought, we did in one day in class, and maybe you would like to copy, emulate what we did to solve another one. Are there any questions? So there is much more for you to do than just focus on the online homework problems. Okay, I want to emphasize that. So I'm going to emphasize it by saying it 5 times today. Okay, but there you go. And a good philosophy to live by when you're in college, like if your professor goes out of his or her way to make some things available to you, you ought to pay attention to it. Those are things I specifically have chosen for the experience we can get solving those problems. Okay, are there any questions? What time is it? We have a little bit of time. Let's go back. Actually, let's go to the video. Right there. And we'll listen to 5 seconds of the commercial again.
Only pay for what you need with Liberty Mutual.
Oh,
I
it's
just
just
said
going
that.
to end.
If you're trying to
now we
lose
get
belly
another one.
fat, stop doing cardio. This sounds backwards, right?
One of the hardest.
Okay, so let's just talk through these 8 series. Someone, I want you to tell me, find one that you think converges and tell me why you think it's so. Okay, anybody? 3 to the n over n factorial, and what test would you use? Somebody want to help him?
The ratio test.
Yeah, ratio test. So here's a rule. When we see factorial, we're going to use the ratio. Now, it's possible it could fail, but that's always going to be where we start when we see factorial. Okay, how about another one? And it does converge. Now, Julian's probably thinking, and if he is, he's exactly right. But if I say, prove it with a test, then thinking this is not good enough. That is exponential growth. That's fast, but factorial growth is faster. Right? And maybe that's what you were thinking. The fact that you didn't have a test right off makes me think you were. But we want to be able to run the test. There are things that we can sort of generalize about, but in the end, we want to pick one of our tests out and run it and prove what we think is true really is true. Okay, what's another one? Yeah, Scott.
-1 to the n times the natural logarithm.
And what do you think it does? Because it's an alternating series, absolutely. The question is, do the terms go to 0 as n goes to infinity? Right, the alternating series has those 2 conditions. The terms have to go to 0 and they have to decrease for a guarantee. What do you think? Yeah, they go to infinity, the log, very slowly. So the alternating series test doesn't settle it for us. Which test does? The terms don't go to 0. Therefore, it diverges by the divergence test. Absolutely. Okay, somebody pick another one. We're going to do all 8 of them.
N over NQ plus 1.
Is it okay if Julian does 2? Yeah, not only is it okay, it's better. Which one?
The one upper right,
Upper right. And what do you think it does?
that would converge.
Converge. And how would you prove it? With?
N over, 1 over N squared.
Yep, perfect. Everything he said is like right out of the book. It's basically 1 over N squared, which converges because it is a with P equal, which is greater than 1. Yeah. Okay, someone beside Julian. Thank you very much. And what do you think it does? Yeah, by what test? Yeah, do the terms go to 0? Yes, the square root goes to infinity. So 1 over it, we're going to go to, see the difference, Scott? Yeah, and they clearly decrease. I mean, the square root of n is greater than the square root of n minus 1. Square root is an increasing function, so 1 over square root is a decreasing. All right, what's another one? Someone. We have to start calling by name. Yeah,
2 to the N minus 4.
what do you think it does?
Well, you use the root test on that, right?
You absolutely can. What do you think you'll get?
2/5.
Okay, this is a very interesting problem. I'm going to write on the board, and the people on the recording won't be able to see it, but hopefully you can hear my voice. So Jesse's exactly right. The root test will settle this issue. We're going to take the nth root of, actually, let's kind of fix it first. The powers are just off by a little bit, and we can fix that. So like I can peel this extra 5 off in the bottom and have 5 times 5 to the n. And then I can add a 2 here, as long as I cancel it out, and then I get 2 to the n. And I gained another 2. Okay, you see how that works? So we're ending up with, the terms of this are 1/10 times 2/5 to the n. Now, take the nth root. And I get the nth root of 1/10. Not quite sure what that does. Times 2/5. Yeah. Oh, I think it's obvious. Yeah. Oh, yes, we can through the sigma and just deal with the 2/5. That's a super good idea. So this guy's not going to complicate. We're going to get. Yeah, so we are ignoring that. We're looking at, yeah, so we're just going to get 2/5, which is less than 1. So it converges. Okay, I'm going to say more about this one, but not right now. We'll come back to it. It converges and the root test settles the issue. How about another one? Yeah. Okay, I said I was going to say something more about this, but Tegan has spoiled my surprise, so we'll work on it now. That one, the second one on the left, is a geometric series, right? And you, by the way, I just wrote it. The terms of it are 1/10 times 2/5 to the n, right? And r is equal to 2/5. Where does it start? It starts at 1. So we're going to get the first term, which is 1/10 times 2/5, right? We're going to grab our 1, plug it in, over 1 minus 2/5. And then I like pretty answers. Probably don't demand them on a test. 50 minus 20. 2/30 converts to a tiny little number. All of the numbers added together, an infinite number of them, make 2/30. So what I was going to ask at the end, but you know, Tegan saw what was going on here. I was going to ask, of all of these on the screen, we only know what one of them converges to. And then I would ask, can you find it? And the answer, it's the geometric series, which is the second one on the left. How about another one? Victoria, have you found one? And what's it do? It diverges by what test? Yeah, the root test. This one's easier. There's not, we don't have to balance the power like we had to do on the Geometric series. Yeah, it's exactly right. The diverges, you can get 3s. If you flip the 2 and the 3, then what? Then it would converge. Yeah, we would get a number less than 1. Daniel, you got one?
You do the one that's the bottom right one, so square root of n.
Yeah, so that's kind of the gnarliest one. It's like in the numerator, that n cubed is going to dominate. So it's like we have n to the 3 halves. And in the denominator, we have basically an n to the 4th. So this is kind of like 1 over n to the 4 minus 3 halves, which is 1 over n. This is 8 halves. So if that's true, what do we think about it? Does it converge or diverge? Converges. How do we prove it? What test are we going to use? Close. We're going to, is it a p-series? No, it's not a p-series because it's got that square root and it's got the minus n squared. But it's like a p-series, so we're going to compare it. Limit compare to this guy right here, 1 over n to the 5 halves. Okay. Now there's one part of that that's a little bit tricky. Maybe we'll talk about it in a minute. Which ones are left? We did all the ones on the right. Oh, the bottom left. Under that play K. There we go. It's the only one left, right? What does it do? Or what test could we use? It's not geometric, at least because of the n in front. Right? I can't write that n in front as some constant raised to the power n. So maybe, but I don't know the limits that we would encounter. The integral test. It's got to be one of them up here. Yeah, and that's the one. X e to the minus x squared. From wherever, 1 to infinity. And then the derivative of the inside is -2. So, yeah. And then we just get e to the minus x squared. 1 to infinity. And that actually converges. So, yeah. When you see the n's, you don't automatically think integral, maybe. But if you write the x's in. We could probably do the second one on the left, the geometric series with the integral test. We could do the top one on the right. I mean, I'm not recommending it at all. We could do it. Are there any questions? Now, listen to this guy's explanation. He talks his way through it. How long is this video? 12 minutes? So now you're ready to go, and you can agree with him or disagree with him if he says, well, this is the way we ought to do it. But it's kind of a nice little example. You're going to use most of our tests. Yep. Are there any questions? If you run into a problem on those pages that I've posted and not quite sure what to do, send me an email or a text. Daniel's about the only one who sends me texts on a regular basis, and I answer them pretty fast most of the time. And, you know, I'll post at the very least a picture of a solution. Anything else? All right, we'll see you Wednesday. I think Math Lab should be open. I want to quit sharing. In the recording.